Okay, we are going to do torque in this episode. As always, if you enjoy this content, like and subscribe. So, a definition in words of torque is the tendency of a force to rotate an object about an axis. But I think it's very, very important to think about torque when we have a net torque, that's going to produce angular acceleration. So that means the object is going to do what? Well, it means that this net torque that's producing an angular acceleration, we can also think of that as changing angular velocity. So it's going to spin faster or it's going to spin slower. But something we haven't talked about yet is angular momentum. Now, that's going to be the next series that we're going to do after this. But we need to be able to talk about angular momentum because that is the result of a net torque. So a net torque produces an angular acceleration, which changes its angular velocity, and therefore it changes its angular momentum. Kind of a weird letter for this, but the letter is a capital L. So, what is the formula for angular momentum? We'll go way more into detail on this later, but I just want to introduce this. Angular momentum is a vector, and it is defined as the radius cross what we can think of sort of as tangential momentum, mv. So we have mr cross mv. And that would be only for a point particle. But if we wanted to deal with angular momentum, let's say of a disk or a ball or a hoop or whatever, then the definition of that is angular momentum is equal to I, the moment of inertia, times the angular velocity. And this would be for any object, not just a point particle. So, just going over this, net torques produce angular acceleration, which changes its angular velocity and changes its angular momentum. But let's go back to the exact definition of torque. So the definition of torque is R, and we did this in the other unit briefly, R cross F. Now, it's important that we do it in this order, because this is a cross product, which means we're multiplying the radius r, sometimes called the lever arm, from our point of rotation, our axis in this case. So you could think of this as a wrench, and you're pushing on the wrench to try to turn a nut or something like that. So we have our radius r, which extends from the axis of rotation out to the force. So here's our force. Now, the torque is this value R times the force that's at 90 degrees. That's what a cross product is. The cross product is the two values multiplied by each other that are at right angles to each other. But there's an added part because this is a vector. So that means that it has a direction. This is kind of confusing because it doesn't seem to really make sense, the direction, but that's only because we think of forces as pushing in a certain direction. So what you have to do to figure out the direction of the net torque is to use something called the right-hand rule. And in the right-hand rule, you take your fingers and you point them in the direction of the radius, and you curve them, bend them at 90 degrees to the direction of the force. The direction that your thumb points is the direction of the torque. So if we have a radius going this way and we curl or bend our fingers this way, our thumb points out towards us out of the page. So that would be the direction of the torque. And that's according to the right-hand rule. And I'll do a couple of examples of that on the next page. So the other thing that you need to know is that the direction of the net torque, that gives rise to the direction of the change in angular momentum, because we said that a net torque gives rise to a change in angular momentum, and the direction of that net torque is also the same as the direction of the change in angular momentum. So we said that to determine the direction of the torque, we need to use the right-hand rule. And because we're working in a two-dimensional surface, we have to be able to discuss how things are moving in the z-plane. And so we can say that something's moving into the page or something's moving out of the page. And the way that we do that is with x's and dots. The x you can think of as the back side of an arrow, and that is going into the page. Whereas a dot is sort of like the tip of an arrow coming towards us, so that is out of the page. So let's say we had something like a vector r going up, and then we indicated a force vector going into the page with an x. Well, what's the direction of the net torque? Well, we take our right hand, point it in the direction of the first vector. This is why it's r cross f and not f cross r. So r comes first, we point our fingers in the direction of r, and then we curve them in the direction of the force, which is into the page. And which way does our thumb point? To the left. So the net torque is left. Now let's do another one. Let's say we're working in a two-dimensional plane where we have r and we have f over in this direction like we did before. Then in that case, we would point our fingers up in r and bend them in the direction of the force, and our thumb points into the page. So again, in this one, the torque would be, like we did on the other page, would be into the page in that case. Now we're going to watch a video to sort of show this in 3 dimensions.
A good example of a cross product is torque, which is the product of r cross f. The cross product is similar to the dot product. However, there are 3 important differences to note. 1. The cross product of 2 parallel vectors will always be 0, and 2 perpendicular vectors will be equal to the multiplication of the 2 vectors' magnitude. This is because the sine of 90 is 1 and the sine of 0 is 0. 2. The multiplication of 2 vectors in a cross product produces a third vector that is at right angles to the other 2 vectors. How are we to represent the direction of this third dimension on a 2-dimensional piece of paper or screen? The convention is to use a dot to represent a vector that is emerging out of the page towards the reader. A trick to enable visualizing this concept is to imagine that the dot is the tip of an arrow that has pierced the plane and is traveling out of the page at right angles to it. An X or cross is used to represent a vector that is receding from the observer and is piercing the plane by traveling into the page. The method for determining the direction of this vector is to use a technique called the right-hand rule. The third way in which cross products are different from dot products is that cross products are not commutative. Multiplying will actually produce the same magnitude, but the direction of the new vector will be different as determined by the right-hand rule.
To determine the direction of the resultant vector, point your fingers in the direction of the first vector, turn them 90 degrees in the direction of the second vector, and your thumb points in the direction of the resultant vector. So we defined torque as r cross f. But there's another definition that we can use for this, and we'll do a little derivation. Let's say we replace, for this net torque, we replace a net force. So that gives us MA. Well, we know from A equals R alpha, A equals R alpha, that we can fill that in and say M times R alpha. So now we have two R's, and we can rearrange that and say mR squared times alpha. And we know that the moment of inertia is mR squared for a point particle. So we can rewrite this as I alpha. So now we can use this expression no matter what I we have. We could do this for a disk or a sphere or a hoop or whatever we want. So the full definition of net torque is defined as R cross F in that order, which is also equal to I alpha. Okay, if we recall back from impulse and change of momentum, that change of momentum is equal to J. And so we know that m delta v is change of momentum, and that impulse is F net t. And so we can rearrange this as we have done in the past to just say m delta v over t. And we know that m delta v, that's change in momentum over time. And if we wanted to do this for the instantaneous value, then we would say the derivative of momentum with respect to the derivative of time. So this formula, when we write this way, F net equals dp over dt, this is Newton's second law. Newton never said F equals ma. He said F net is equal to the rate of change of momentum with respect to time. So what if we take this formula and multiply both sides by r? Well, if we do that, we get r cross F net on this side, and on the other side we get r cross dp dt. Well, this momentum at a radius is angular momentum. So we can rewrite this, because we know this is net torque, R cross F, put in net torque for that. And then this becomes dl, the derivative of angular momentum, with respect to time. So what is this? This is the time rate of change of angular momentum. And where did this come from? What produced this? Well, net torque produced this. So we do have to be careful in some later problems. You're going to see this come up. If the net torque is 0, well, what does that mean? It means that the change in angular momentum is 0, or we could say L remains the same. If there's no net torque, doesn't mean no torques, no net torque, then L can't change, whatever that happens to be. Okay, and if we have, we're doing this for a problem where we have a system, if the net torque of the system, so we might have multiple things in this system, a ball and a rod or things like that. Then again, if the net torque of the system is 0, then L of the system must remain the same. Another subtlety with torque is that we are the ones who choose the origin. So let's look at two different examples where we can choose two different origins. The first one is where we have a ball rolling down a hill with friction. So it's not slipping, it's not sliding. Well, we can say that the sphere, or the ball, whatever, is rolling around this point. So it's sort of rotating around that point at any instant in time. It's kind of a tricky idea to get your head around. But if that's the case, then we don't have, even though there's friction acting here, that friction is at R equals 0. So that frictional force here, Ff, does not produce torque. However, we know that when we break up these forces, we get Fg sine theta. So we can call that mg sine theta. And that's acting at radius r. So the way that we could write this equation would be net torque equals I alpha equals r cross mg sine theta. So we can do that, but remember that the moment of inertia at this point would be about this point, not about the center. So what we would have to put in for I, we would have to use pat to figure out the new moment of inertia, I. But what if we decide to pick this point, the center, as our origin, and we can look at the force of friction acting from this point? So then this time, that's going to be our torque from here to here. And so our net torque would be I alpha is equal to R cross FF. This time, I would be about the center of mass. So if this was a solid disk, that would be 1/2 mr squared. Whereas here, it would be 1/2 mr squared plus md squared to do that using the parallel axis theorem. Another couple of subtleties that we have to look out for is what if we have a system, and we're going to do some problems like this, where we have a fixed hinge. So in this case, the ball comes in and hits this bar that's just free to swing there, and you can picture the bar is going to swing up. But the question is there a torque? Well, there is a force in this direction due to the push of the ball at a radius r from the fixed hinge. The hinge gets a force in the other direction, but that force is at radius 0, so that does not produce a net torque on the rod. And the last subtlety that we have to look out for is that the force may not be given perpendicular. So in this case, we have a hinge. This can rotate in this direction when it gets pushed on by this force, but not all of that force is perpendicular. Remember, it's a cross product. So what would the net torque be in this case? Well, it would be net torque is equal to R cross FP, and then we need this component right here, which would be Fp cosine theta.